Hi everyone, and welcome back. In this video, I'm going to be going over question 3 of the 2015 AP Physics 1 exam. Now, you may be wondering why I decided to skip question 2, and that's because that question covers the content of electricity and magnetism, which is no longer required on the AP Physics 1 exam. However, if you still want to go over that question, then you can go to College Board's website where they have a whole storage of past exams along with their solutions and scoring guidelines to get a more detailed idea and answer to that question. But I'm just going to be skipping over that question in this series because it is no longer a required portion for the exam and it is no longer tested. So for this question, which was worth 12 points with a suggested time of 25 minutes, we're given a block that is initially at position x equals 0 in contact with an uncompressed spring of negligible mass. The block is pushed back along a frictionless surface from position 0 to negative d, which compresses the spring by an amount of delta x equals d, and then it's released. And at x equals 0, the block enters a rough part of the track and eventually comes to rest at position x equals 3d. And there is a coefficient of friction between the block and the rough track that is given as mu. So for part A, we're asked to sketch and label. Remember to sketch and label the graphs because you're going to lose points if you forget to do one or the other, obviously. But a lot of people forget to label the graphs, so make sure you label the kinetic energy and the potential energy of the graph if you're asked to do so. So we're asked to sketch the kinetic energy and potential energy as a function of the position of the block between negative d and 3d. So we don't need to calculate the values, but we need the same vertical scale for both quantities. Okay, so let's start with the potential energy, just because I feel like it's a bit easier given our initial conditions. So we know that it was compressed by an amount of d. So that would give us our maximum total energy of the block spring system for that segment. So we can choose just one point, let's just say here, and that will indicate that axis on the y-axis, that intercept, will be our max energy for this segment of time. So we also know that the potential energy should be in a curved line because it's going to decrease, and it's related to x as x squared. So let's draw a curved line all the way down to the origin. And here from the origin, when it reaches x equals 0, it no longer is in contact with the spring and it's unstretched. So that means the potential energy is going to be 0 for the rest of the way on, all the way up until 3D. So we can just draw a line all the way up until 3D where it is equal to 0. Now moving on to the kinetic energy. Now we don't know the specific velocity values for our block, but we do know that in this system on the frictionless part, energy is conserved, so the total energy must remain constant, which means that we can draw the curved line, basically the inverse of the potential energy for that segment up until x equals 0. So let's just draw kind of like the potential energy flipped over. And now when it reaches the friction part of the surface, we're going to have a linear function for the kinetic energy from the origin to 3D, and it's going to be decreasing. So we can draw a line decreasing from the origin up until 3D. And then remember to label your graphs. So this one was the kinetic energy, And then this one here was the potential energy. Okay, now we are moving on to question B. So we're given that the spring is now compressed twice as much to 2D, and a student is asked to predict whether the final position of the block will be twice as far at 6D. And they reason that since the spring will be compressed twice as much as before, the block will have more energy when it leaves the spring, so it will slide further along the track before stopping at position 6D. So question part B, part 1, asks us which of the aspects of the student's reasoning, if any, are correct, and explain how we arrived at our answer. So, looking at their reasoning, we can see that the student did say correctly that the block will have more energy when it leaves the spring because it is compressed more. So that part of their reasoning was correct. So it will slide further along the track. That part is also correct, but it isn't considered part of the reasoning, so you don't have to specify that. And now it asks us which aspect of the reasoning, if any, are incorrect. So the student reasons that since the spring will be compressed twice as much as before, it will slide further along the track at 6D, which is twice as far as it was originally. And that's the part that was incorrect. The incorrect reasoning is that the final position of the block will be twice as far as 6D because of the compression that was twice as much. Because the spring's energy does not scale linearly with its compression. Okay, now in part C, we're asked to use quantitative reasoning, including equations if we need, to develop an expression for the new final position in terms of D. So we're going to move down here, and we know that the maximum energy of the system is given by the initial spring potential energy. So initially, in our first trial, let's label the potential energy as U1. We had U1 equals 1/2 times KD squared, where D is our compression, which means that U2 is equal to 1/2 K times 2D squared. And 2 squared is equal to 4, so that gives us 4U1. And then we know that the work done is equal to the force of friction times the distance that it traveled across the frictionless surface. So in the first case, we have work 1 equals the force of friction, which is the coefficient of kinetic friction, times the normal force on the block, which is simply its weight in this case. And we multiply it by the distance it traveled, which is 3D. And then the work done in the second case by the force of friction is also equal to mu mg, but this time we're given a delta x2. But we don't know x2 because we're trying to find x2 in terms of D. So we know that W1 equals U1 because at the end it loses all of its energy. So here W1 equals U1, and then W2 equals U2, which equals 4U1. So that means that W2 is equal to 4W1. And now we can substitute the friction and the displacement that we had originally to get that mu mg times x2 is equal to 4 times W1, which was equal to mu mg times 3D. And looking at this, we can get that x2 is equal to 12D. Okay, so now we're done with part C. And in part D, we're asked to explain how any correct aspects of the student's reasoning are expressed by our mathematical relationships in part C, and explain how the relationships in part C correct any incorrect aspects of the reasoning as well. And we're asked to refer to the relationships in part C, not just the final answer we obtained. So I'm going to do it verbally here because there's a lot to write down. Obviously on the AP you'd have to write it all down, but I'm just going to explain it a little with words here. So we know that the student was correct when they said that the block has more energy in the second case, expressed by the calculations here that compare the initial energy in the spring. In this case, we had 4 times as much energy as we did in the first case. And then the student was also correct in reasoning that the block will slide further because the equation for work shows that the work done by friction to stop the block in the second case is greater than the work done in the first case. However, it also shows us that the student was incorrect in reasoning that the energy increases proportionally with the spring's compression factor. They reasoned that it would increase by a factor of 2, but we showed here that it would increase by a factor of 4. So that is it for question 3 of the 2015 AP Physics 1 exam. Thank you for joining me today, and I hope you learned something new.